Hello, everyone. We are Group 1, and in this presentation, we're going to be going over what we did for Project 3. So first of all, we're going to go through a little bit of an overview of what data sets we used and the pre-processing we used, and then we're going to go into discussions of our two methods we chose, and then we're going to have an overall evaluation and analysis at the end. So yeah, moving into the data sets and pre-processing. So the data set we chose was TinyImageNet 200 clean. So this contains thousands of images categorized into 200 different classes. All of the images are 64 by 64 in size. And then this data set is made up of only the RGB images from the original TinyImageNet dataset, which is in itself a smaller version of the ImageNet dataset. And then we split our data into three different sets: the training, validation, and testing data. So for pre-processing, we first resized images to 256 to enlarge the features. Then we cropped them to 224 by 224 to capture the most important features, and then applying with the expected image size for both models. Then we normalized the images, and then finally we used data loaders and created those for each dataset split.
Now, for our first method, we implemented GoogleNet or Inception v1. This method was first introduced in the paper Going Deeper with Convolutions in 2014. It's a deep convolutional neural network trained on the ImageNet dataset, and it was designed for image classification and detection tasks. The architecture is based on Inception, meaning it uses various operations such as 1 by 1, 3 by 3, and 5 by 5 convolutions, as well as 3 by 3 max pooling to process inputs in parallel. This allows GoogleNet to maintain a high degree of accuracy while reducing the computational complexity. And we chose this method over more modern versions like Inception v4 because it takes less resources to train, fitting better for our purposes. For the training, we used the pre-trained GoogleNet model from PyTorch. We utilized transfer learning to retrain just the final layers of the model using the TinyImageNet dataset we mentioned before, which this process involves freezing the weights of the base model and only training the newer layers so we could use the features from the main training. And this allows us to train much faster compared to training from scratch. Now, in terms of how the model performed in training, this was our best model for the 2e negative 3 learning rate for our hyperparameter. Uh, it saw at best around a 38.8% accuracy. And this is how the graph looks compared to training loss. Next slide. And this is what our hyperparameter tuning looked like. So we tuned the learning rate over 20 epochs of training. We found that GoogleNet met its maximum accuracy at epoch 16 for the 2e negative 3 learning rate for an accuracy of 38.8%. Um, and a good note is that the ideal learning rate is probably somewhere between 2e negative 4 and 2e negative 3, somewhere in that range. Next slide. This is also the training loss over epoch, and as you can see, it converges quite quickly in the 2e negative 3, but it's probably more in the ideal range, somewhere between 2e negative 4 and 2e negative 3.
I'm John. I'm going to be discussing method 2. So for our second method, we used MNASNet, which was first introduced in the paper MNASNet Platform-Aware Neural Architecture Search for Mobile in 2018. It's also a convolutional neural network that was optimized for mobile devices, and similarly to GoogleNet, it's designed for image classification and detection tests. MNASNet's architecture is based on inverted residual blocks, which were first introduced with MobileNet v2. And this architecture allows MNASNet to be more memory efficient compared to traditional residual networks. And what inverted residual blocks bring is it essentially compresses the input features to a lower dimensional space, which allows for the model to more efficiently perform the computations on the input. And this just makes the model a lot more lightweight, which is why we chose it for our use over other similar models like NASNet, which we were originally considering. But since MNASNet is just more lightweight and it's less expensive to train, we thought that it would fit better for our purposes. So for training, we use the freely available pre-trained MNASNet model from PyTorch's TIM library. And this model was trained on ImageNet, which if you recall from earlier is essentially just the bigger version of the tiny ImageNet that we're using for training. And we also use transfer learning to train this model as well. So that was done by freezing the weights of the earlier layers and training only the final classification layers of the model. And what training the final layers does is essentially just adapts the model to the tiny ImageNet dataset. Since the tiny ImageNet dataset only has 200 classes in it, and the original ImageNet dataset has 1,000 classes, we had to adapt the model to that in order for it to properly make the correct predictions in classes. So here's our validation and validation accuracy and training loss for our best model. As you can see, over 20 epochs, the loss drops very sharply in just the first 3 epochs, and then it kind of stabilizes throughout the rest of the time. The accuracy also kind of reflects this loss. You can see within the first 3 epochs, it rises very sharply. And then we have our best accuracy at the 5th epoch, and then it starts to stabilize after that. Next slide. Here is just a graph of all the validation accuracies we had for each learning rate that we used. Learning rate was the hyperparameter that we were tuning. And you can see that 2e negative 4 starts very low with accuracy, but it steadily rises and it keeps rising. Whereas with 2e3, it starts fairly high, but it peaks very early at epoch 5 and then starts to go down. So from this, we can gather that the most optimal learning rate would be somewhere between 2e negative 4 and 2e negative 3. And then with 2e negative 2, you can just see that it's very stable throughout. So there's not much convergence actually happening with that. Next slide. And here's just the training loss for each epoch. You can see 2e negative 4 starts very high and then drops very quickly, but then it stays fairly stable throughout the rest. 2e negative 3, which was our best model, starts pretty high and then drops very low. And then 2e negative 2 starts at like a very balanced spot, but then it does drop lower, but overall this model was not as good as 2e negative 3, possibly due to some overfitting issues.
Hi, my name's Jason. I'll do evaluation and analysis. So when we look at class accuracy for GoogleNet, we examine the distribution of its class accuracies. We see that the lowest performing class drops around 25%. These are the classes where the model struggles the most, either because the images are like similar or because the features didn't distinct for GoogleNet. For GoogleNet, the maximum accuracy is around to 80 to 90%. These highly accurate classes are typically the one that the network can learn efficiently. Most of the classes here fall between 45 to 65% accuracy, which tells us that it's reliable across majority of our dataset. Now for a MASNet, it shows similar spread in terms of minimum and maximum accuracies, but you can see that there's some difference in behavior. Just like GoogleNet MASNet has a minimum around 25% and a high peak between 80 to 90%. One thing that's different is that MesNet has slightly fewer classes, reaching a higher range. This means that it can perform well, but it doesn't generalize quite as strong like as harder classes. Same thing, accuracy falls between 45 to 60% range, but we see that the distribution for MasNet is a bit more uneven. Some mid classes bounces up and down, but this is typically normal for our lighter models. Um, During the classification accuracy, GoogleNet reached a smaller, higher accuracy than MasNet. And then during validation, MasNet performed better, reaching 39.2% compared to 38.8% for GoogleNet. This suggests that MasNet was generalized slightly more effective on validation split. And we move to the actual test data set. GoogleNet achieved 38.4%, while MasNet fell very closely at 38.2%. However, the overall performance gap between them is only a small difference. And this is our project.